All right. We're going to look at two organic families today. The first organic family is an alcohol, and I'm going to apologize. This video is not going to be done in real time. So, what that means is there's a note on the screen. I'm going to talk about the information in the note. But I'm not writing it out as the video progresses. So, what that means for you is you need to maybe like hit pause, write down what you see, and then listen to what I have to say. Okay. So, alcohols are a type of organic family that are characterized, I guess, by this functional group called a hydroxyl, which is basically an OH that's bonded together, attached to a hydrocarbon chain. So we can see here that I've shown a hydroxyl bonded to an R, which represents the parent chain. Okay, so when you have this hydroxyl group right here bonded to a carbon chain, you have to indicate that that hydroxyl group is there. Just like we have to indicate there's a methyl group or a double bond or a chlorine bonded to the hydrocarbon chain. And to do that in the name, when you're naming, they get the ending ol, O-L, okay? Just like alcohol, it has the ending ol. It's important to note here that the hydroxyl group can be on any carbon in the chain. So it can be on any carbon in the chain. And what you do is you indicate position with a number. So I have a couple examples right here for you to look at. So these are two really simple examples. We indicate position of the hydroxyl group, just like we indicated position of the double bond. So with the number, and then the ol here. So this is a butane 2-ol. And again, the but tells us that there's 4 carbons. The and is telling us it's all single bonds, and a 2 on carbon 2 is the hydroxyl group. Okay, and just the same right here, hexane 3-ol. Super easy and straightforward. Another example, so maybe make sure you have those down. Another example is this one right here. Example where we see that we have 3 hydroxyls. Because we have 3 hydroxyls, our name has to reflect that. So the name for this one is prop because we have our 3 carbons, and because they're all single bonds. And then it's 1, 2, 3 triol. And so we use the tri to indicate that there's 3 hydroxyls. If there was 2 hydroxyls, it would be a diol. If there was 4, it would be a tetraol. Probably will not see a tetraol. Okay. Now, sometimes an alkene or an alkyne can also be an alcohol. So that is an example of this one that we see here. Now, when it comes to numbering, an hydroxyl group would get a preferential number over an alkyl side chain, so over a methyl or an ethyl, but the double bond takes the lowest number over anything else. So the double bond gets the lowest number, and then if you had to like break a tie, then you would give the hydroxyl group the lower number over a methyl group. Okay, so that is why this is carbon 1 here instead of this being carbon 1, because we want to give the double bond the preferred, it gets preferential treatment when it comes to numbering. So you could make yourself a note in this space if you wanted to, that the double bond gets the lower number. All right, So because we've added now a hydroxyl group, a oxygen and hydrogen bonded together attached to a carbon, we've really significantly changed the properties of a hydrocarbon. So hydrocarbons, we haven't talked a lot about the properties of those yet, but I will give that to you. But if we look at these two examples here, and I want you to kind of ignore the information I've written in green and pink. Our propane is carbon bonded to hydrogens. And if you go back and you think about what we learned about polar bonds, that this is all non-polar bonds. So propane is non-polar bonds. It's completely symmetrical, actually. And so that means it's a non-polar molecule. And so it has properties reflective of a non-polar molecule. And this is all going back to our grade 11. But as soon as we add the hydroxyl group, I just realized I'm missing some hydrogens here. As soon as we add this hydroxyl group, things are going to change, okay? Because now you have some polarity happening. The bond between the carbon and the oxygen, this is very polar. And so is this. This is very polar. And in fact, if we think about the molecule having like a positive side and a negative side, like this is definitely going to be slightly negative over here. And this part of the molecule is going to be slightly positive. Okay. So the addition of our hydroxyl group results in the molecule becoming polar. It's no longer symmetrical because you have this OH here on the end. It also has those polar bonds. So this propanol is polar. Okay. It's unsymmetrical and contains polar bond. And we remember that from 3U, that's the criteria for our polar molecules. Now, the other thing that is really important here is that because of this polarity, this hydroxyl group is capable of hydrogen bonding. Okay, so I'm just going to scroll up so we can see this. So remember that a hydrogen bond is the really strong intermolecular force between molecules. Okay, it's the strongest one. The criteria for a hydrogen bond is that it has to have a hydrogen and a fluorine, oxygen, or nitrogen. So this propanol up here, it can hydrogen bond, whereas the propane cannot hydrogen bond. So this hydrogen bond means that this propanol is capable of hydrogen bonding with other propanols. So they're more strongly connected. And so if you remember to grade 11, we talked about how that hydrogen bond, the polarity of a molecule, impacts solubility, and it impacts like melting point and boiling point because it requires more energy to break apart the molecules, which is what has to happen for melting and boiling. And then the ability to hydrogen bond is what allows some things to be soluble. So by adding this hydroxyl group, you went from something that was non-polar, so it's going to have a relatively low melting boiling point, and it's going to be insoluble, to something that's going to have a higher melting boiling point, and that is going to be soluble, so dissolvable. Okay. Now, just remember, though, that this propane, it still has some intermolecular forces. It's capable of the London dispersion force, that really weak intermolecular force. So there's weak attractions between molecules, which is why propane is basically a gas that you put in a cylinder, in a tank to barbecue. Okay. So just remember that now you are changing the polarity of your molecule, and you're now having something that is more strongly attracted to other molecules and water. Okay. If you need a reminder on bond polarity and intermolecular forces, you need to jump into the 3U reference site and go look at those lessons. Okay. So now that we've talked about how this hydroxyl group results in polar molecule, let's look at properties that result from that. And I've actually kind of talked about some of them already. So one of the properties is that our physical properties of alcohol, they're going to have a higher boiling or melting point than the comparable alkane. Again, because you have added polarity. You have something that is polar, whereas the alkane is nonpolar. So we've got ethane versus ethanol. You can see that. The alcohols is more soluble in water than the comparable alkane. Okay, this is because when we already talked about this, the polar molecules are soluble because of the ability to hydrogen bond with water. Now, the other thing though is that the longer the hydrocarbon chain, the less soluble. So methanol is going to be more soluble than octanol. And that has to do with the fact that it's like a lot more non-polar, and because there's more London dispersion forces existing between longer chains than shorter chains. And I'll try to find a video on this for you. All right, so those are some physical properties of alcohol. And then we'll look at a couple chemical properties of alcohols before we finish. So chemical properties of alcohol, big one is that they're combustible. They burn as a clean fuel. If you combust an alcohol, you don't get a sooty residue like you would with incomplete combustion of hydrocarbons. They react with these things called oxidizing agents that produce other functional groups in a reaction. So the alcohols are really a starting point for making a lot of other organic families. And another reaction or chemical property is that they react with a concentrated sulfuric acid to produce water and a double bond. And you have seen this before because this is just a dehydration reaction. Okay, it looks something like this. So you can go from an alcohol to an alkene by dehydrating, taking off the hydroxyl. And I've shown that you take a hydroxyl and a hydrogen and you make this right here. What happens is these two electrons go to bond the hydrogen to the hydroxyl, and then these two electrons swing over and become the double bond. Finally, the one thing that we need to look at is that we can form alcohols from a hydration reaction. So it's basically the polar opposite of dehydration. So in dehydration, where we take away the hydroxyl and an oxygen to make water, in hydration, we're going to basically do exactly the opposite, where we have an alkene and we're going to add water to make an alcohol. And I'm going to really hope my stylist is going to cooperate on this one. So let's take a look at how to do this. All right, here we go. All right, so hydration, going from an alkene to an alcohol. Your parent chain is going to stay the same. So you're going to have 5 carbons. That's not going to change. So we're going to draw those in, hopefully. 1, 2, 3, 4, 5. All right. I always leave hydrogens off until the end. What happens, if we take a look, is this double bond here, those electrons are going to be used to connect a hydrogen. And you have to remember your Markovnikov's rule that we looked at during reactions, and that the rich get richer. So the atom, the carbon with the more hydrogens, is going to get the hydrogen. So the hydrogen is going to come onto this carbon right here. And then your hydroxyl right here is going to end up on this carbon right here. And that's, again, you have to remember that Markovnikov's rule for the rich get richer. So the carbon that already has the most hydrogens is going to get the hydrogen in a hydration reaction, and you know this already. I just want to add my hydrogens because it'd be really bad communication if I did not. But my stylist is not working well, which is why I'm not writing this lesson in real time. So I think you're just going to write in these hydrogens, and I'm going to keep going because this is just ridiculous. Okay, so this is just showing you the hydration reaction of going from 1 pentene to pent in 1. Oh no, I lied. It's pentan 2. That hydroxyl is on a 2. All right, we got that fixed. So then the last kind of chemical property that is important for alcohols actually leads us into our next organic family, because 2 alcohols can undergo condensation reaction to make an ether and water. Okay, so if we have a methanol, which we see right here, and a ethanol, which we see right here, they undergo condensation. So condensation means that it releases water and bond those 2 carbon chains together to make this structure, which is called an ether. So ether is our next organic family that we're going to talk about in our next lesson, which I think you're actually doing right away. But just to point out, our ether is a hydrocarbon chain with an oxygen and another hydrocarbon chain. Okay. Mom? Yep. Remember that package you ordered? Yeah.